In this video, we will go over what are transport processes, why we study transport processes, and how can we succeed in studying them. As chemical engineers, we use processes to convert raw materials and energies into products. And these processes are usually many interconnected steps represented pictorially by flowsheets with many unit operations. The original chemical engineer education is the study and design of flowsheets for industrial processes. Shown here is the famous Haber-Bosch process that converts atmospheric nitrogen to ammonia by reacting with hydrogen using finely divided iron metal as a catalyst. This process is responsible for more than 170 million tons of ammonia produced each year globally. 80% of them are used in fertilizers, and this process consumes approximately 1 to 2% of the global energy. The block flow diagram on the right shows how we use nitrogen from air and hydrogen and react them and finally get into a liquid ammonia final product. And this block flow diagram focuses on the overall process. We want to learn more about what are the equipments that are responsible for each of these processes. Then we need to use a process flow diagram shown here that shows each unit operation used in the process. For example, in this process, we can see we have reservoirs, we have compressors, mixers, heat exchangers, reactors, absorbers, coolers, and condensers. And each of these unit operations can be reused over multiple times, where the principles of the underlying calculations in designing them are usually very similar. Because each unit operation uses very similar underlying principle for designing them, instead of just designing the overall process, chemical engineers also starts to look at each unit operations. For example, we can look into each heat exchanger and found out that very similar processes happen within each heat exchanger. Therefore, chemical engineering education gradually shifts from just designing the overall process into looking inside each unit operations. Shown here is a shell and tube heat exchanger that changes the temperature of the process fluid. Because each of these heat exchangers work very similarly, after we know the specifications of the inlet fluid temperature and the outlet desired fluid temperature, we should be able to design a heat exchanger that matches our specification. Therefore, in addition to studying and designing processes, chemical engineers also study and design unit operations. When chemical engineers start to optimize these unit operations, we must understand the underlying mechanism of how things are being transported within these unit operations. For example, how are fluids being moved, how are mass being transported, how are heat being transported. Therefore, in addition to studying these unit operations, we are also interested in studying the transport phenomena that underlies these unit operations. Shown here, for example, is the inside of a shell and tube heat exchanger, where we have cooling water flowing inside the middle tube. And in the concentric tubing, we have hot gas that is a mixture of nitrogen, hydrogen, and the reaction product. We would be interested in the temperature profile, that is, how this temperature changes with respect to the radius, T of R. And we will also be interested in the cooling water's velocity profile, that is, how does the velocity varies with respect to R. And these would be the subject of transport processes or transport phenomena. And in the future, chemical engineering research frontier is expanding from these transport phenomena into understanding what are the molecular mechanisms in developing these type of profiles, and that is the realm of nano and molecular engineering. So we have seen here how chemical engineers has evolved from looking only at flow sheets to look at also unit operations, the underlying transport phenomena, and finally wanting to understand the molecular mechanism with nano and molecular engineering. From these evolutions, we can see three levels of studying transport phenomena. The first level is on the macroscopic level. In the macroscopic level, we're concerned mostly in the flow sheets and the unit operations. And we usually use the macroscopic balances as equations that guide us in solving these problems. The length scale we're working with is usually on the centimeters to the meter scale, and that is 10 to the minus 2 to 10 to the 0 meters. The second level is on the microscopic level. On the microscopic level, we are usually interested in a smaller scale, that is usually on a micrometer to centimeter scale, or 10 to the minus 6 to 10 to the minus 2 meters. The equation that guides us on the microscopic scale is usually the equation of change. And finally, we have the molecular level. On the molecular level, we are more concerned on the molecular mechanism, on how these transport phenomena happens. And that we're usually working with a length scale of 1 to 1,000 nanometers. That is 10 to the minus 9 to 10 to the minus 6 meters. We will be using all these three levels to study transport phenomena on the macroscopic level and on the microscopic level in solving different problems. What exactly are the transport phenomena? Transport processes is defined as the study of how physical quantities move and exchange. It is also known as transport phenomena. We are more concerned of the transport of momentum, what usually called the momentum transfer, or fluid mechanics, the transport of energy, or usually called heat transfer, and the transport of chemical species, or usually called mass transfer. The transport of momentum, energy, and chemical species is the three most fundamental transport processes that we will be studying. However, we can also study other types of transport, such as the transport of electrical charge, that is very important in batteries and solar cells. Ideally, we want to study the transport phenomena together because of several reasons. First, the transport of momentum, energy, and chemical species usually occur simultaneously in processes. They rarely occur on themselves. They also share many fundamental equations, so we can solve similar problems with similar solution methods by analogy. In addition, many of these transport processes share very similar molecular mechanisms, so we will look at them all together. Studying transport phenomena might be slightly boring because there's a lot of applied mathematics and applied physics. But it is so fundamental that transport processes is used in so many industries that is not only in chemical engineering but also beyond. For example, in chemical processing industry, petroleum engineering, the design of batteries, solar cells, and electrocatalysts, manufacturing of computer chips and electrical components, polymers and composites, pharmaceuticals and biotechnology, nanotechnology, and far more applications. Having a good grasp of transport processes is a prerequisite to be a successful engineer in these areas. So how do we succeed in studying transport processes? Mathematically, you should be very familiar with differential and integral calculus. We will be doing calculus in almost every class. You should also be proficient in solving elementary ODEs, or ordinary differential equations. That will be very important. You're also expected to have a good intuition of multivariable calculus, so that when we are talking about things in 3 dimensions, we have a good mathematical language in describing them. More important than the math is the physical intuition that you will develop throughout this course. You want to explicitly note and make appropriate assumptions that is appropriate to the engineering situation. And what counts as an appropriate assumption will require engineering judgment that you will build throughout this course. And second, always visualize the physical system so that it gives you context about what the problems that you are solving. When you arrive at the result, always note the physical interpretation of the result Ask if they are consistent with your physical intuition. Do the numbers and the unit make sense to you and the problem? With these tips, let's start studying transport processes.